behave in noise. The receiver front end is modeled the same way as all the other receivers we previously considered. Now the received signal plus filtered additive noise goes through a limiter discriminator. What is limiter discriminator doing? The limiter is for taking care of amplitude variations due to the channel. And the discriminator is a differentiator. Now, even if you implement the system using something like a PLL or feedback-based modulator, at the end of the day, the discriminator action is taking care of the demodulation of the FM. Okay, because the signal, remember, is integrated and put into the phase. So, and of course, there's a low pass filter after the limiter discriminator to remove the high frequency components, and we get our signal. So ideally, this will work. I mean, no matter how you implement it, of course, in practice, there's going to be a feedback loop, etc. But we can model the FM receiver as such, because we're talking about the mathematical analysis, noise analysis anyway. Okay, so this is my input signal into the receiver with the time varying phase, and the message is here inside this time varying phase. And ideally, this time varying phase is the integral of my message. Now we will assume that our message is band limited, such that its power spectral density is limited to W, as before. Let's compute SNRB first. Well, interestingly here, the message power has no effect on the signal power, right? Because at the end of the day, my message is this sinusoid. I mean, I'm sorry, my modulated signal is a sinusoid and the message is buried into the phase, right? So the noise, the signal power is AC squared over 2, no matter what the message power is. Okay, what the message power is, as you know very well, affects the beta, affects whether the FM is narrow band or wide band, etc. We're supposing that has been taken care of appropriately. Okay, what is the noise power? As before, it's N not W, because we're looking at noise power in the message bandwidth. And our carrier to noise ratio is AC squared over 2N not W. When we're talking about FM, in contrast to AM, it makes more sense to call the baseband SNR the carrier to noise ratio, because the signal itself looks like a carrier. It's a cosine. Okay, SNRO. Now, how are we going to do this? First of all, let's think about the bandwidth that we are admitting. Okay, in SNRB, remember, our job is easy. It has nothing to do with the type of the modulation in terms of the computation of the noise, because in the noise computation, we're computing the amount of noise power in the message bandwidth. For SNRO, though, we will have to compute the noise power in the modulated signal bandwidth. The modulated signal bandwidth in FM depends on the beta of the FM. And from Carson's rule, as you know, we have the approximation that the bandwidth is 2 times delta F plus W, or twice beta plus 1 times W. Okay. In the wideband case, it's approximately 2W, but this case is not interesting because it's identical to conventional AM, so no need to analyze that. Now, let's consider the passband noise or bandpass noise as before in terms of a time varying amplitude and the time varying phase. Now, this noise has been added to our incoming signal before the limiter discriminator, right? Because before the limiter discriminator, we have the same RF front-end structure as in amplitude modulation types. So some bandpass noise has been added on top of the bandpass signal. And we can use a phasor diagram to compute the net effect. I mean, how to combine the amplitudes and the phases. The phasor diagram is going to make this easier. Okay, so this is our signal. AC is the amplitude. I mean, AC is the original carrier amplitude, and theta is here. Let me take this. Let's see, this is going to work. There's a selection, there's supposed to be a selection tool. I don't think it's this one. It didn't work very well. Anyway, so we're talking about AC cosine WCT plus phi of t plus AN of t cosine WCT plus phi n of t. Okay, the noise is this red vector, okay, and the angle of the noise is this phi n of t. Now, when the SNR is large, the red vector is much smaller in magnitude with respect to the black vector. What is AX? So AX of t cosine WCT plus phi x of t refers to the resultant vector that forms out of adding the black and the red vectors, right? But under the highest order approximation, we can make the approximation that this phi n, okay, this difference, okay, this angle here, which is phi n minus phi, is approximately the same as this angle. So we are making the assumption that the blue and the black are almost parallel. Okay. I mean, eventually, when the noise is small enough, they're going to be almost parallel. So if they're almost parallel, then this angle and this angle are the same, which means we can compute this height using this height, let's call it h of t, using this angle phi n minus phi. First of all, phi x, which is this the phase of the blue resultant signal, is of course equal to phi of t plus phi difference. Okay, we are not directly assuming phi difference is 0, but we're sort of using another approximation saying this angle, this angle and this angle are the same. So now, when x of t, the signal, is input to the limiter, the amplitude variation is removed. Okay. The discriminator performs differentiation, which is basically differentiating phi x. Okay. So if there was no noise, then the derivative of phi x, what is phi x? Phi x is this. Derivative of phi x, in the absence of noise, phi d is 0. So the derivative of phi x is derivative of phi, which is kf m of t. In the case of noise, we are differentiating phi plus phi d. The first term is going to give kf m of t. The second term is going to give us the derivative of phi d. What do you see here? Additive noise. Okay. So the additive noise, we've been able to achieve additive noise because of modeling this angle phi x as phi of t plus phi d. But then, what is phi d? Okay, we need to make an approximation for phi d in terms of the other known parameters. Okay, now when the SNR is high, AC squared is larger than AN squared most of the time, and phi d in magnitude is much less than pi most of the time. So we'll go back to that h of t height in the triangle. Okay. Now focus on this h of t. And we made the approximation that this angle is equal to the phi n minus phi t. So then h over AC is equal to sine phi d. Well, approximately, right? So h of t over an is the sine of this angle, which is approximately equal to phi n minus phi, which is phi d. Okay. So this angle is approximately this angle, and this angle is phi n minus phi. And but then one moment, let's see. This is right. What is phi d is this angle. Okay. So I was using the wrong triangle. Let's go back and let me erase all of this. So let's take a look at this. This is h of t. This is phi d, right? So h of t over AC is equal to sine phi d. And now we're going to assume phi d is small. So phi d is approximately equal to phi d. I mean, sine phi d is approximately equal to phi d itself. Right. So But similarly, from the other triangle that I was struggling with just a moment ago, from the other little triangle, h of t is approximately an sine of pi n minus phi. Okay, that makes sense. Now, from those two things, we reach the approximation that phi of d is approximately equal to an over ac sine phi n minus phi. Okay, what are we trying to do? We're trying to express this noise term in terms of things that we know. So at the moment, we've expressed the noise term in terms of the sign of the noise minus, oops. Sign of the noise, phase of the noise minus the phase of the signal. Okay, so now let's go back to this sine phi n minus phi. By the way, what is phi d? Phi d okay, by the way, so let's now use some trigonometry. I'm sorry, let's use some trigonometry. I'm going to expand this sign of the difference okay, as sine phi n times cosine phi, okay, minus cosine phi n sine phi. And an of t and ac are as before. So let me write this actually, an over ac sine phi n minus phi. So I have an over ac sine phi n minus phi. And all I've done is apply trigonometry to expand this sine of the sum of the two angles. Okay, but what do you see? It's as if this is our carrier, if you will, and NQ and NI are the in-phase and quadrature component with respect to this angle phi. At least we can model them as such. So, renaming an of t sine phi n of t as NQ and an of t cosine phi n of t as Ni, we have this representation for phi d. Okay, where is our message? Message is in here. Okay. So notice that the additive noise is the derivative of phi d. That's what we're trying to get at. 1 over 2 pi d by dt phi d of t. Now we're going to go a little bit more into this adventure of doing approximations. We want to understand the power spectral density of this additive noise. Okay, if we can find the power spectral density of phi d, the relationship is simple because it's a linear time invariant operation from one to the other. Okay, so now bear with me for a little bit more. The autocorrelation function of phi d is where we start because we want to find the power spectral density, right? So write the expression phi dt plus tau times phi d of t and take the expectation. Well, what is phi d? Remember, phi d is well, phi d is one over AC and Q of t cosine minus 1 over AC and I of t sine phi of t. So take 1 over AC out of the expectation as 1 over AC squared. Okay. And Q of t plus tau times cosine and Q of t times cosine. We're going to have 4 terms. We're going to have ni of t plus tau, ni of t sine phi t plus tau sine phi t, and we're going to have cross terms like this. Cross terms. The cross terms are going to disappear from the expectation because ni and nb being uncorrelated. Okay. So as a result, we have 2 terms remaining. The first term is expectation and Q of t plus tau and Q of t, which is the autocorrelation of the quadrature noise component. This is multiplied by expectation of cosine t plus tau times cosine phi of t. And similarly, we have the autocorrelation of the in-phase noise component times expectation sine of phi t plus tau, sine of phi of t. Okay. So since R and I and Q and R and Q and I are 0, we will have these cross terms disappearing. And as we have computed before, Rni and Rnq are identical to Rn. We haven't really computed them, we've discussed them, borrowing the results from the textbook without proof because they were done in 306. Okay, so as a result, when we plug in Rn of tau in place, what do we find? We find that our phi of tau, phi d of tau, the difference phase noise component, is 1 over AC squared Rni of tau expectation cosine phi t plus tau minus phi of t. Okay. Now, a little bit more approximation is unfortunately needed. Notice that these are the power spectral densities of the in-phase and quadrature noise components. They're like, I mean, ideally, they're like a rect function. Okay. But, so this means that the corresponding autocorrelation is going to look like a sinc function. Okay. Now, how about the bandwidth? As you know, there's a duality between frequency and time. Bt over 2, which is the end of the passband here, end of the bandwidth here, corresponds to, what is this? Corresponds to the 0 crossing of the sinc pulse here. Now, phi of t itself, the phase due to the message, is relatively slow with respect to Bt. Because the bandwidth of the message is W, if beta is large, say beta is 5, for example, we're talking about beta plus 1 times W for Bt. In fact, twice beta plus 1 times W for Bt. So Bt is much larger than W. Okay, so that's why when we talk about the PSD of phi of t and the corresponding autocorrelation function, the autocorrelation function is relatively flat within the time frame that Ni is oscillating, within the time frame of the duration of the impulse response that corresponds to this filter characteristic. In other words, since this impulse response really is not an impulse response, but it is an autocorrelation function, the autocorrelation function decays to 0 before this autocorrelation function changes. Okay? So this means that the noise becomes uncorrelated before this phi of t changes. Okay, so within the range of tau, where our Ni of tau is significant, the autocorrelation function is flat. It's approximately equal to its value at 0. Okay, which means approximately phi of t plus tau is equal to phi of t. In other words, this thing, our phi of t of tau, which is equal to Rni of tau. So let's go back and see this approximation that we're doing one more time. We're basically saying that R phi d is approximately equal to Rni. And therefore, the power spectral density of this noise, additive noise, is equal approximately to the power spectral density of the in-phase noise that is scaled. Okay, let's go back to the limiter discriminator output. Remember, we had this noise. Now we're going to substitute with Ni. But there's going to be filtering due to the differentiation. And that's the main point that I want you to focus on. The shape of the noise is changing. It's no longer going to be looking like white noise. Okay, so this is our limiter discriminator output. The message plus the derivative of the phase difference, phi d. This is my additive noise. I've just approximated my way into showing that the PSD of this additive noise is approximately given by the PSD the PSD of phi d is approximately given by the PSD of Ni. And now, since we have differentiation here, it's j2 pi f squared divided by 2 pi squared. As a result, I have S and D of f being equal to f squared Sni of f over AC squared. So this f squared term causes this interesting behavior in the additive noise. The original Sni is flat. The effective noise, additive noise on top of the signal is multiplied by f squared. So lower frequency components have attenuated noise. Higher frequency components have high noise. Okay, so FM has this interesting phenomenon where the noise at high frequencies is amplified. Okay, this is very interesting. And after all of this very seemingly strange approximations, the resulting noise PSD that we ended up with, number one, is pretty correct for high SNR regimes practically. Number two, it is very easy to analytically express. It's simply N naught over AC squared F squared. Okay, very simple. So the higher the carrier amplitude, the lower the noise, which is nice. But of course, there's going to be caveats for all of this to be valid. And the noise is increasing toward the band edges. Now, let's try to compute SNR out. The demodulated signal looks like this, and we need to compute signal and noise components, power of the due to the signal and noise components. The signal power in the demodulated signal is clearly kf squared PM. How about the noise power? The noise power can be computed by integrating this strange bowl-shaped noise PSD that we have from minus W to W. So it's minus W to W and not over AC squared F squared DF, which is 2N not over AC squared W cubed over 3. Okay, notice that as the received power increases, okay, this term is reduced. Okay, as the received power increases with AC increasing, the noise and out is reduced. Okay, so let's put S out and N out. Let's take the ratio KF squared PM over 2N naught over AC squared W cubed over 3, and we find the output SNR for FM to be 3 AC squared KF squared PM over 2N naught W cubed. Okay, W cubed, interesting. So the SNR goes down rapidly with the message bandwidth. It increases fast, again, it increases rapidly with the carrier power. Also increases with message power, clearly. How about the figure of merit? The baseband SNR was already computed at AC squared 2N naught W, AC squared over 2N naught W. So the figure of merit is interesting. It has to do with KF squared in the numerator. So the larger the KF, the larger the figure of merit, which is good. And it goes down with the message bandwidth. But by the way, this is all valid in the high SNR regime. There is going to be a threshold effect in FM that we're going to see in a minute. By the way, let's find an equivalent expression for the figure of merit in terms of beta. Notice that KF, we can think of, so delta F is the frequency deviation, which is KF AM. But KF, what is AM? AM is the maximum magnitude of M of T. Let's think of a normalized sort of KF that absorbs the maximum magnitude of M of T. So that essentially, which corresponds to normalizing the message size such that its maximum magnitude is 1. So we can redefine KF to be scaled such that we can treat the maximum amplitude of the messages as 1. So the figure of merit, remember, is 3 KF squared PM over W squared, but KF is equal to delta F, so we can represent it in terms of beta as 3 beta squared PM. Oh, so as beta increases, the figure of merit increases quadratically. Okay. Now, of course, in this notation, maximum message amplitude has been scaled as 1. So PM is also limited. So it goes like 3 beta squared, essentially. Okay, let's do an example. Suppose M of T is just a cosine, single tone, with a PM, which is a half. The figure of merit is 3 beta squared over 2 then. Okay. So if delta is 75 kilohertz, like commercial radio, W is 15 kilohertz, beta is 5. The figure of merit is 3 times 75 divided by 2, which is 37.5. 10 log 37.5 is 15.7 dB. Okay. Remember the figure of merit for double sideband or single sideband? It was 1. Now we're going from 1 to 37.5. That is a major improvement. So now you're seeing why FM is such a big deal, in radio broadcast at least. And this is not, in fact, not factoring out that we can take care of that bowl-shaped noise. And we will see now a way of dealing with that, which will improve the SNR even more. Okay, but before, just a word of caution. Notice that the preceding analysis has been based on the high SNR assumption, which is that the noise amplitude is much less than AC. Okay. And that Ni squared plus Nq squared is much less than AC squared most of the time. And expectation of N squared is much less than AC squared over 2, which means AC squared over expectation N of T squared is much larger than 1. Notice that AC squared over 2 is the carrier power. Okay. And expectation N squared is the average noise power at the limiter discriminator input. We can define a carrier to noise ratio as AC squared over 2 N squared. AC squared over 2 expectation of N squared of T. Okay, so this is the carrier power, and this is the noise power, carrier to noise ratio. Now, we'll see some restrictions on this rho for our high SNR assumption to be valid. Now, first of all, let's represent. So we found our figure of merit as 3 beta squared PM, right? This is only valid for the carrier to noise ratio to be much larger than 1. What is the relation between the carrier to noise ratio and SNRB? SNRB is AC squared over 2 and not W. Rho is AC squared over expectation n squared. Well, expectation n squared has to do with BT, right? BT is 2 delta F plus W. Okay, so 2W beta plus 1. So therefore, expectation of n squared, the power of the bandpass noise, is n naught over 2 times 2BT, which is n naught 2W beta plus 1. Okay, so rho is AC squared over 2 n naught W times 2 beta plus 1. Okay. And SNRB is this. So what is the relation between SNRB and rho? Rho over SNRB is 1 over 2 beta plus 1. Now, then, this figure of merit that increases quadratically with beta is valid only if SNRB over 2 beta plus 1 is much larger than 1. If it goes below 1, there's an FM threshold effect. So the quality is enhanced as beta increases only if SNRB is small enough, large enough. So if you keep increasing beta, yes, you do increase IFM, provided that SNRB is large enough. Because if you're increasing beta, but SNRB is small and it cannot keep up, and if this is violated, then you're going to run into an FM threshold effect where this is not going to be valid anymore. Let me erase all of this and say it again. So, because of the beta squared here, we see that the quality is increased as beta is increased. But then notice that as beta is increased, rho drops. So in order for rho to continue to be larger than 1 as beta is increased, SNRB has to be sufficiently high. Okay. If not, there's going to be an FM threshold effect as seen in this picture. In this picture, we see SNRB in the horizontal axis. Okay. And we see output SNR in dB scale with respect to different values of beta. Beta equals 3, beta equals 5, beta equals 7. Now, why is the output SNR in dB scale increasing linearly? In this regime, the increase is linear. Why? Because if we're in the high SNR limit, remember, SNR out is 3 beta squared PM times SNRB. So in fact, let's go back. SNR out SNR out is increasing like kf squared, and SNR O over SNR B is IFM, and IFM is increasing like beta squared. So that's why the difference between beta equals 3 to beta equals 5 to beta equals 7 look linear, because this is the dB scale. Okay. And now, but after a while, as SNRB is reduced to below a certain value, okay, for each beta value, there is a certain point at which SNRB is too small, such that this is no longer satisfied. That point is going to be reached earlier for large values of beta than for small values of beta. So the threshold effect is encountered earlier when your beta is large. So that means if you want large beta, yes, you can get a good figure of merit with large beta, but you need to ensure that you're above the threshold, and the threshold is larger with large beta. Now, experimentally, the carrier to noise ratio being larger than 10 is good. It means you're good. Okay, and there's a constant slope after SNRB larger than 20 beta plus 1. Okay. In dB scale. Okay. So let's do an example. What is the required received power in an FM system with beta equals 5 if W is 15 kilohertz and this is the noise PSD, 10 to the minus 14 over 2, right? Now, the power of the normalized message signal is 0.1 watt. That is PM, where maximum M of T is 1, is 0.1 watt, and the required SNR after demodulation is 60 dB. So SNRO is required to be 60 dB. Notice that SNRO is figure of merit times SNRB, and we showed that well, we essentially showed that, let's go back. SNRO is this, 3 AC squared KF squared PM over 2N naught W cubed. Okay, and KF can be replaced in this case with delta F, and delta F over W is beta, so that's why we can arrive at this expression. So check this as homework. Now, the output SNR is required to be 60 dB. What is 60 dB? 10 to the 6. Beta is given to be 5. Message power is given already, and not is given, W is given. So from that, you can simply arrive at the received power equal to twice 10 to the minus 5, or 20 microwatt. Okay,